Welcome back to the next video, everybody. Today we got a wild one for you. We're going to look at the Langlands reciprocity conjecture. We're going to go global today. So what is the Weil group of a number field? Let's let F be a global field. The Weil group of F, W sub F, which always exists, which isn't really obvious by the description I'm going to give, but you can see Tate's number theoretic background for more discussion on that, is a group that maps surjectively onto G sub F and admits a canonical isomorphism from its abelianization to the invertible elements in the adels of F mod F star. Remember, F star embeds here. And for each place V of F, there is an injection of what we call the local Weil group of F at V into WF, which defines a map from rho to what we'll call rho sub V, maybe like a kind of big global representation to a local representation at V, from the two-dimensional semi-simple representations of the Weil group of F to those of the local Weil group of F at V. Okay, so these global representations give me local representations. Okay, and so you can see Tate's number theoretic background, as I said above, for more details on the existence and basic properties of this guy. Now, if I give you this row here, almost all of the local row sub B's are unramified. And sort of conversely, the unramified row sub B's do uniquely determine rho, essentially by strong multiplicity 1, which is covered in a previous video. What is global LRC for n equals 2, which is the case we'll care about? Well, using LLC for GL2, of course, I can attach to any semi-simple row of the Weil group of F to GL2 of C, a global representation pi of rho of GL2 of the adels of F. And we'll call that representation pi of rho, and we'll give it local components pi of rho sub V, tensoring over the places V of F. So conjecture for now, Langlands reciprocity. Suppose F is a global field. So now we have a global statement, not just a local statement like we covered in the last video. Suppose I have a representation rho from the Weil group of F to GL2 of C and that it's irreducible. Then there is an actual automorphic cuspidal representation pi with local components pi sub B of GL2 of A sub F, such that the local components pi sub B here of this pi match the local components pi of rho sub B of here of the representation pi of rho of GL2 of A sub F that we already know exists by patching together local Langlands information. Okay, so I can sort of equate this representation pi of rho that I already know exists in a meaningful way with an actual automorphic cuspidal representation. And these things will kind of agree locally everywhere. All right, so in particular, I won't talk much about L functions at all, actually, but the so-called L function attached to pi, which is just the product over the primes V of the local L functions, is known to be entire, and it must actually equal what we call the Artin L function, L of S rho attached to rho. And that L function is also a product of local L functions at each place V of F. And you can see Jacques Langlands for details and definitions about this kind of stuff. I don't want to get into this. Okay. A remark that I really should make is that this conjecture we just made is equivalent to Artin's conjecture for two-dimensional irreducible rho. I will be discussing Artin's conjecture very briefly later. And so all that is to say is that the LRC is sometimes called the strong Artin conjecture for that reason. Okay, do we need equality up here everywhere? That's the next question. It will be convenient to check it almost everywhere, and as a matter of fact, you can. So proposition 1, let F be a global field, and suppose rho is a two-dimensional representation of the Weil group of F. Let pi be a cuspidal representation of GL2 of the adels of F. Then pi sub B, the local component of pi, is equal to pi of rho sub B for all V, is a statement that's equivalent to the following statement. The trace of the local Langlands class of pi at V is equal to the trace of rho sub B of prob sub V for almost all V. In fact, I can even tell you which places. It's the places V where these local components pi sub B and rho sub B are unramified. Okay, so this equality in LRC can actually sort of just be checked for almost all V in a very meaningful way that it attaches itself to prior information we learned in other videos. And the proof of this is really just strong multiplicity 1. It's not hard. And if you go back and look at all of my videos from this chapter on Langlands tunnel, and you look at the earliest version of LRC that we stated, you see immediately that proposition 1 plus the version of LRC that I stated just above on a previous slide immediately imply this earliest version of LRC. All right, let's circle back to new forms because that's really what we want to be studying here. Let's suppose rho from GQ to GL2 of C is irreducible odd representation, and let pi of rho denote the corresponding automorphic cuspidal representation of GL2 of the adels of Q under the LRC. So we're assuming the LRC holds right now. We do not actually have it. It's conjectural at this point. Okay. Then pi of rho corresponds via our bijection between the new forms f and the associated representations pi sub f. This bijection was covered in my classical versus modern theory video, if you'd like to go back and review that. To what? Well, pi of rho is going to be one of these guys. That's the claim. And which new form is it? Well, it corresponds to a new form f with Fourier coefficients. Let's call them a sub n. Where does this new form live? That's the first thing. It lives in S1, which is crucial. It's weight 1. It's 4 gamma 0 of n with character psi. What is n? N turns out sort of miraculously, or very nicely, let's say at least, to be the conductor of rho. To every one of these representations, there's a number called a conductor, which I discussed quite some time ago in like chapter 1 of my notes. The conductor of this representation matches the level of the new form, which is awesome. Psi is determined essentially by the central character of pi of rho. Okay, so there's a nice connection there. And what is the defining property of this new form f? The pth Fourier coefficient a sub p is nothing but the trace of rho for b sub p for almost all primes p. Look familiar? This is one of, if not the defining property of the Galois representations attached to new forms that we discussed oh so long ago back in chapters 1 and 2 of my notes. Okay, so this needs to be proven. This is kind of a big deal. I'm not going to do that. You can see Cornell, Silverman, Stevens, page 180. But I will point out one thing. If you remember, we had this issue. We had a loophole, kind of a long-standing issue that we wanted resolved. We were not able to use the results that we have discussed so far to actually guarantee that the new form that we get in the conclusion of automorphic Langlands tunnel actually has weight 1. Well, guess what? We just solved the issue. Proposition 2 gives me that weight 1. Okay, so that loophole's been closed. So closing remark, and then I'll sort of say what we need to do still. In Deligne-Serre, the authors associate to each new form f with Fourier coefficients a sub n in S1 gamma 0 of n psi, an irreducible two-dimensional rho of GQ with conductor n, so the conductor matches the level, an odd determinant psi, so psi matches the character, such that trace of rho for b sub p is a sub p for almost all primes p. Fantastic. What does that tell us? If you take that information, if you take the Deligne-Serre construction, they call it the Deligne-Serre weight 1 construction, if you take this together with the LRC that we just stated for f equals q and rho odd, plus proposition 2 here, what you find is that new forms of weight 1 are exactly the same thing as irreducible odd two-dimensional representations of the absolute Galois group of q satisfying Artin's conjecture from above, which is awesome. It gives you a whole new perspective on new forms. You can just think of them as the same thing as very special representations of the absolute Galois group of Q. Okay, so what do we need to do still? So I claim that if you take all of the information I've given you so far in this chapter, you can easily see that global LRC for n equals 2 automatically implies all versions of theorem 3 that I have given you from the chapter, and that it also implies, maybe together with propositions 2 and 1 here, automorphic Langlands tunnel, immediately, essentially, if you believe all of the results that I've given you so far. And we can't get too deep into this Langlands theory because we have to keep moving. This isn't actually a video series on the Langlands program. That's a whole separate ballgame. But if all that's true, and if our weight 1 issue has been resolved, which it now has been, doesn't it just really suffice to prove this conjecture here? We just need to prove LRC in the case F is Q, in the case the representation factors through the Galois group of Q, in the case it's odd and solvable. If we can do that, we will have met our entire goal for the chapter. So next video, we're going to make some intermediate remarks and look at some examples relating to all this. But then in the following video, we will begin collecting the results needed to actually prove that special case of LRC that we just got done talking about. Okay, so I will see you then. Thanks for watching.